Okay, everybody. I have received a couple of requests to work a few problems on homework. So I'm just going through and kind of randomly selecting a few problems out of the probability homework. And this is what I've come up with. I'm going to do page 203, numbers 11 and 24, and page 211, number 18, and page 225, number 16, and number 28. Now, several of these are even, so the answers are not in the back of your book, so maybe that'll help you. But some of them may not have been assigned, so I'm just kind of picking problems that I think represent the kinds of problems that we have talked about and are doing on homework, and just kind of randomly picking them. So, if they're not homework questions I assign to you, that's okay. They'll still give you some examples of the kinds of problems that we have talked about for probability. So here goes. All right, number 11 on page 203 in my book says 2 coins. Before that, the directions say, and you always have to read these directions in this book. It's a little bit tricky sometimes. So for example, exercises 11 through 20, use the theoretical method to determine the probability of the given outcome of event. State any assumptions that you need to make. So we're going to just do the math, basically. So when they say to use the theoretical probability, that means do the math. You know, if they said use the experimental probability, that would mean go out and actually do whatever it is. So this one is 2 coins. Tossing 2 coins and getting either 1 head or 2 heads. Find the probability 1 or 2 heads when you toss 2 coins. Okay. Now, there are a ton of ways you could do this problem, but I think that probably the easiest way to do it is to go ahead and just list out your outcomes. For instance, I know that I could toss the first coin and get tails and tails. First coin's tails, second coin's tails, right? That's one probability. The second, or outcome possible, okay, the second outcome is I could get tails and then heads, okay. The third outcome is switch those, right? The first one is a head and the second one is tails. And then the fourth outcome is that they're both heads, right? So this is called my sample space. Okay, these are all the possible outcomes that I could possibly have, and they want the probability of 1 or 2 heads. Okay, well, how many outcomes are there whenever I throw 2 coins? 4, right? 4 possible outcomes. And this one has 1 head, this one has 1 head, and this one has 2 heads. So that means that my probability here is 3 of them have 1 or 2 heads out of 4. 3 out of 4. Okay. Now the assumption there is what? That we're using a fair coin. All probabilities of heads is 1/2. Okay. Now, and I only say that because they asked me to list out any assumptions, and we know that that's what we're assuming is that we have fair coins. All right, moving on. Number 24, new set of instructions. This set of instructions says, exercises 23 through 30 involve complementary events. In each exercise, find the probability of the given event. State any assumptions that you use. So remember that complementary events mean not whatever, okay? So whenever we say complementary, it's like the opposite. It's not going to be whatever they told me to do. And normally, it's not, like say, if the outcome was A, so if we said, what's the probability of getting heads? Well, the probability of getting heads is 1/2. What's the probability of not getting heads? Well, that's also 1/2, right? But the way we find that is 1 minus the probability of whatever the thing was, right? Whatever that original thing was. Okay, so that's going to come in handy while I'm calculating complementary events probabilities. Okay, number 24 says, what is the probability, that one was dying on me. What was the probability of not drawing a heart? A heart. From a standard deck of 52 playing cards. Okay. And I'm just going to ... it. Okay, so not drawing a heart from a standard deck of 52 playing cards. Okay, well, first we have to find the probability of drawing a heart. Probability of getting hearts is what? Okay, remind me, what kinds of hearts can you have? You can have an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, right? So if you remember, each suit in a deck of cards has 13 cards. So the probability that I will draw a heart, there are 13 hearts out of how many? 52, right? Okay. Or we know, if you're really thinking and you want to make your numbers smaller, there are 4 suits and one of them is hearts, right? This will reduce down to a 1 in 4 chance that I'll get a heart. Okay? So there you go. You've got a 1 in 4 chance that you're going to get a heart. All right. But that is that I will draw a heart. The question was, I will not draw a heart. Okay? So that's a little bit different. Remember that notation for complements is you put the solid bar on top, and this is literally red. This is the probability of not hearts, or the complement of hearts, but we're going to say not hearts. Okay, and in that case, we're going to use this little thing that we put up there, and we're going to say 1 minus the probability of hearts. Okay, but we know that the probability of hearts was 1/4, right? 1 out of 4. So 1 minus 1 out of 4 is 3/4. Oh, that's funny. It's the same answer. It's a coincidence. All right. There you go. So that's some basic probability stuff. Hopefully that helps with that section. The next section was page 211. Let me leave that right there, just in case you're still writing. Page 211, number 18. Let me grab that page. Oop, too far. Okay, page 211. This guy is about the law of large number and expected value. Okay, so whenever, let me back up. I don't even see directions on this section, so that's cool. Number 18 says, New Jersey's Pick 4. In New Jersey's Pick 4 lottery, you pay 50 cents to select a sequence of 4 digits. 50 cents to play. Okay, think about that for a second. If you're the one playing and you have to pay 50 cents, is that a positive or negative? Okay, hopefully you're saying negative. Okay, so it's a negative 50 cents. It's leaving my money, leaving my hand. Okay, you pay 50 cents to select a sequence of 4 digits. And they give an example. Your example could be 2273. Yours could be 5555. Whatever they are, 4-digit number. Okay. Those are my examples. Okay. And then they tell me that there are 10,000 different possible 4-digit sequence. Why are they telling me that? 10,000 possible outcomes, right? That's my total. That's how many ways how many different combinations I could get whenever I do this Pick 4 lotto. Okay? If you select the same sequence of 4 digits that is drawn, you will win. Okay, value for winning is $2,788. It's a pretty good little thing for only having to put it in 50 cents, right? Okay. So if you win, then that's pretty good winnings for one. But what's your chance? You pick some 4-digit number. Say I picked 5555. You picked a 4-digit number. What's your chance? What's your probability of winning that $2,788? You picked one sequence of numbers, and there are 10,000. So it's a 1 in 10,000 probability that you'll win that, right? Okay, so it's not very likely that you're going to pick the one 4-digit sequence that actually wins. But it's possible. Okay, and then what it says is, what is your expected value? And in the long run, how much do you lose for each 50-cent bet? Okay, so let's think about this. Absolutely, positively, if I play this, I'm going to lose 50 cents. Does everybody agree? Okay. So for sure, I've got a negative 0.5. And sometimes they'll say, multiply that by 100%, okay, or by a 1, because that absolutely happens. You have to lose your 50 cents. You have to pay to play. If you don't pay, then you're not going to win at all, okay? All right, so then what? Okay, plus, everybody loses 50 cents. What? Somebody's going to win, right? Okay, if you do, remember that for expected value, it's always the value times the probability plus the value times the probability. And they put little subscripts here, right? The value for the first outcome times the probability of that first outcome. Well, everybody pays 1, or pays 50 cents, right? So that probability is a 1. Okay. The value of the second outcome, well, what's that guy? If we win $27.88, right? Okay. Times the probability of that second outcome, which, by the way, if you lose, you just stop right there, right? You just lost 50 cents. Okay. But if I win, then it's this much times 1 out of 10,000, because the probability that I'll win is a 1 in 10,000 probability, or chance, some people will say. Okay. All right, so what does that mean? This, I'm out of space there. I'm sorry, so I'm coming down here. Negative 0.5 plus, you can put this on top, 2788 over 10,000. Okay, so whenever I think 1, 2, 3, 4, 1, 2, 3, 4, because that's just 10,000, right? So I can just move. Negative 0.5 plus a positive 0.2. I'm going to make that an 8. Is that okay with everybody? 7, 8, 8. But I'm dealing with pennies here, right? Since pennies, dollars, cents, C-E-N-T-S. So instead of saying 2.2788, I've made that 28 cents. Okay? All right, so what does that mean? I'm going to lose 50 cents, but I could win 28. So my overall expected value is negative, because the 50 cents was negative. This is positive, but it doesn't overweigh it. Negative 22 cents. So you're expected to lose 22 cents every time you play that lottery. Just expect you're going to lose it. Okay. Now somebody's going to win, but most people are going to lose. All right. So that's the idea of expected value. Maybe that helps. Okay, moving on to page, 225, number 16. 225, number 16. See what I got. Okay. All right, this guy, this is one of those probabilities that has a combination going on. So they're going to use this particular chart here, or table. Probability in court decisions. In exercises 15 through 20, use the data in the following table that summarizes the outcomes of guilty and not guilty pleas in 1,028 criminal court cases. Remember that 1,028 because it's going to be important, because why? That's my total. Okay, so we're going to do that. What I'm going to do, because I don't want to hold this book up here, is I'm just going to take a second to reproduce that table so we can look at it. Okay, and here's what it says. These in the top row are sent, or the middle, I guess I should say, sent to prison. The bottom is not sent to prison. Up here is guilty plea. This is not guilty plea. And my numbers are 392 in this first column here, 564. And under not guilty, my numbers are 58 and 14. Okay? And here's what number 16 says. What is the probability that a randomly selected defendant either pled not guilty or was not sent to prison? Now let's think for a second. When we think either and or, remember that that's an add situation. But because these are combination problems, we have to subtract out the overlap. Okay, so remember that's the intersection. So this is a union problem, it's an or, so I'm going to add, but I can't double count. Okay, so again, number 16 said, what is the probability that a randomly selected defendant was either pled not guilty, so that's this column right here, I'm going to highlight it so we can see it. Okay, pled not guilty, or they were not sent to prison, not sent. Here. Okay, there we go. All right, so here's what happens there. Remember, I'm going to figure out this column plus this row, and I'm going to add all that together. So I've got 58 plus 14, out of, and we'll talk in a second. And then here it's 564 plus 14 out of. Now we could be careful and know right now that the intersection is the 14, but I'm going to go ahead and actually subtract that off. So I'm going to minus the 14 out of. Okay. Now my question is this: what is the number that should be on the bottom? That's the total, right? Okay. And remember, I pointed that out. There was 1,028 cases total. Okay. So doing a little real quick math here. This is a 12 carry, 72. Plus, that's an 8, 578 out of 1,028. Minus the 14. Okay, and if I do some arithmetic there real quickly, that should be 636 out of 1,028. This plus this minus that. The bottoms all stay the same because they have a common denominator. Now, as I've said before, I'm fine if you want to leave that as a fraction right there. However, I will tell you that I know that this is 0.619. Okay, so if you go ahead and make that into a decimal, that's fine. Or you could say what? 61.9%, right? So almost 62% of people either pled not guilty or they were not sent to prison. Okay, so take it easy whenever you're reading these. Just be careful. I'm going to do another one because I want to make sure we've got this particular concept, because I think sometimes these combination problems bug people. So we're going to do another one, and be sure you look at those charts and you really, really know what's going on there. Okay, the other one I said was 28. Let's look at 28. Okay, again, they've got a table, so let me try to reproduce it pretty fast. It's kind of a wider, longer table than the other one. I need, let's see, 4 rows. And then I need 1, 2, 3, 4, 5 columns. Okay. So, looking at it, let me throw you a shot of it right here. This one is about drug allergies and placebos. I'm sorry, allergy drugs. Don't go backwards. And what it says is, in a clinical trial of an allergy medication, 120 people are treated with the medication, and 100 other people are given a placebo. There's a control group. The control group consists of 80 people who are given neither the medication nor the placebo. Okay? The number of people in each group who showed improvement appears in the table below. All right. So there's my thing. I'm just going to fill in my table real fast. This is improve. This is no improvement. This is a total line down here. And I think that they're probably just throwing in the total line so that we can compare and make sure we really have everything correct. Across the top, this is allergy drug, placebo, control, and total. All right. And here are my numbers. 65, going down this column, 55 and 120. The placebo is 42, 58, and 100. And the control is 31, 49, and 80. And then my totals over here are 138 and 162. And the total right here in the corner, this is 300 and this is 300. So everything should add up correctly. All right, so number 28 is actually a 3-part problem. So let's look at it and see what we got. A says, if 2 selections are made with replacement, so we're going to have to talk about what that means again, find the probability that both people improved. Okay, so let's just look real quickly at both people improved. Okay, improvement is here. Okay, so how many people improved total? Right over here, right? 138. Okay, so here's what it says. You go in and you pick somebody, okay? Randomly pick out of the whole 300 people. And then you replace that person. It says with replacement. So I go in, I grab somebody. What's the probability that I'm going to find one person there? What's the probability that I get somebody with improvement? Well, it's 138 of those people, right? So 138. And what's that out of? What's the total? 300, right? Okay. So this is the probability that I randomly select somebody in this group and I get somebody who improved, right? That's what they wanted, improve. Okay. But they don't want just that. They say, what's the probability that if 2 selections are made with replacement, the probability that both people have improved. Now, both means multiply, right? We want this one and we want that one. Up here, this was or. Oops, sorry. This was or, right? That's why we added. But this is and, so both means multiply. So I'm going to multiply this by whatever I get next. Okay, with replacement. So I pull this guy out at random, one person, and I get 138 out of 300 probability that I will get somebody that's improved, okay? But I replace them. What does that mean? Okay. If I put that guy back in the population here for me to pick from, do I change any of my probabilities? The answer is no, because I put him back in. I replaced him. So that means that everything stays exactly the same. Nothing changes. What kind of situation is that? Is that independent or is that dependent? This guy right here is independent of the first one. It does not matter what happened the first time I pulled somebody out of that group. It does not matter because I replaced it. So it's an independent event and nothing is going to change. So the question was, find the probability that both people improved. So what's this probability? It's still 138 out of 300, right? Okay. So you can multiply that and multiply that straight across. You should get approximately 0.212 when you divide it out. I'm not going to do that math by hand. I'm cheating a little bit. Sorry about that, because I happen to know the answer. But you can multiply straight across the top, straight across the bottom. The bottom's going to be a 9, 1, 2, 3, 4, 4 zeros. So is that 90,000? Okay. Divide it out, and you should get 0.212. Okay. That's the first part. Part B. Part B says, if two selections are made without replacement, find the probability that both people improved. So this one's a little more catchy, because the probability for the first guy I pull having improvement, that's still the same, 138 out of 300. Okay, that's no big deal. But the deal is I kept that guy. Okay, I'm not putting him back in. So when I go to pull my second one, and again, it's an and situation, I want both people to have improved. Okay, what's going on here? How many people are left in the pool once I pull one of these out? It's only what? 137, right? Because I did not replace. So the number on the top changes. And what about the total number? I kept one of them, right? So is it still 300 people in the pile? No, I kept one. So how many are there? 299. Okay. So this guy right here is dependent. The second probability changed based on what happened in the first draw, the first time I pulled out of that pile. Okay, so again, I'm not going to do all that multiplication. You go straight across the top, 138 times 137, straight across the bottom, 300 times 299, and then you'll divide those. I am going to tell you that that should be a 0.211. Okay, so look at that, and what do you think? They're really, really close. And that's probably because my sample size is pretty small here, right? It's only 300 people. But are they the same? No, they're not the same, right? So because they're not the same, we have to think about what's going on here. Okay? So C says, compare the results from parts A and B. Okay? Well, they're really close, but not the same. They are different. Okay. And what happened? In the second problem, the probability of getting someone who improved was changed dependent on the first draw. Okay, I'll say its outcome. So whatever happened in the first one, its outcome changed my second probability because I'm dependent in that case. The second probability is dependent. All right, so that's about it for that. That's 30 minutes worth of questions from the homework. I hope that helps some of you guys out. If you have still yet questions, please let me know. I'll be glad to meet with you and talk to you. All right, have a great one. Thanks.